Hello, good evening. Within this session, we're going to be building on a model we had previously built to illustrate the ways in which common health economic structures can be incorporated into agent-based models implemented in the AnyLogic platform. Within this model, we had a stylized population which progressed among several states of diabetes. There we go. And over time, the quality of life of individuals as they progress through successively larger, later and more serious stages of their conditions, quality of life declined, cost per year is generally exerted or generally rose, and there was also a cost associated with a transplant operation, which, in contrast to a cost per year, was sort of a cost for a particular event, a particular operation. We then further had a depiction of the population as a whole, where this population of these people was used to derive quality some common health economics measures, namely life years lived, number of years lived by that population over time, the integral of the population over time, a measure that is sensitive to changes in mortality, for example, that shorten people's lives, that cut their lives short, and quality adjusted life years, a measure which take into account not only the length of life but also the quality of life. As the WHO said, considers not only adding years to life but life to years. Our model further took into account costs, both in a sort of simple undiscounted fashion that doesn't consider the time value of money or discounted cash flow, and a version where discounting is applied. We apply principles from discounted cash flow, net present value, bringing future costs into the present through discounting, and essentially taking the net present value of cash flows. This is based on the time value of money ideas, the fact that a given smaller amount of money now can turn into a much larger amount of money later. And so if we consider the present value of future monies, we need to discount them to reflect the fact that if we had some costs born later, we could pay those off by putting a smaller amount of money into the bank now or other reliable investment in such a fashion it will grow during that subsequent time to be that larger amount later, sufficient to pay off that larger amount later. So we have this model which computed quality adjusted life years lived, undiscounted costs, cumulative, discounted costs, cumulative, for given scenarios. And we could run this model with several scenarios. For example, a baseline scenario where we had I should have mentioned that within these costs, we considered two types of costs: costs borne through the provision of health services, for example, medications that would need to be provided to an individual by the healthcare system, costs associated with operations such as transplant operations, with perhaps diagnostic equipment or blood glucose meters for diabetics, medication, as I said, like insulin or metformin. We're a bit fast and loose here with the perspective we're taking. You consider this from a societal perspective or from a narrower perspective, payee perspective, but fundamentally we're taking into account costs from health services, but we're also taking into account costs from interventions. So the idea here is that we may have some scenarios which represent interventions, and specifically sort of in line with the stylized design of this model, we considered only one type of intervention here, one that would enhance the chance that a pre-diabetic would, before developing diabetes, would go back to a normal glycemic state through some sort of lifestyle change or other investment. So they lose their pre-diabetic state, recover as a full normal glycemic individual. So when we investigate, we had parameters associated with those interventions, and specifically there were two parameters. One, sort of a screening costs to spot individuals among all non-diabetics, people known not to be diabetics. How much cost is being borne per year to try to find pre-diabetics, and then some cost to undergo lifestyle changes for those pre-diabetics who are identified. Now, for a baseline, we assumed essentially no intervention, and thus we assumed that that there was no chance per year that individuals would go back from a pre-diabetic state to a normal glycemic state due to the intervention, and there were no costs per year associated with the intervention. By contrast, we had a scenario where we sort of modeled with cost estimates that are not grounded, purely stylized. We had some chance, and the idea being that if we had a pre-diabetic and an average of approximately 4 years, they could actually, on average, go back to a normal glycemic state, and we would also have some cost borne by that individual on a per-year basis. Cost borne for searching for such individuals among non-diabetics, on a cost of $200 per non-diabetic out there, and then a cost for those pre-diabetics of a cost of $5,000 to invest in lifestyle changes that would give them this strong chance of going back to a normal glycemic state. So in short, we had a baseline scenario, we had an intervention scenario, which simulated a situation where we had invested heavily in pre-diabetes, in diabetes prevention through helping pre-diabetics. So we could run, for example, the baseline scenario, and we see these quantities of quality-adjusted life years and life years in these undiscounted cumulative costs and discounted cumulative costs accumulating over time. And as the number of individuals in the population declines due to deaths over time, we're following for example, a cohort here. We could very easily trivially, we could add an open population where people are coming in. There's nothing privileged about the cohort, but for simplicity, we used a cohort formulation. We didn't have births and deaths. We didn't have deaths. And as the population declines over time due to aging, at the individual level, as people progress through these states, for example, this individual being in a pre-diabetic state, we had a costs accumulating, undiscounted costs, as well as discounted costs here. It looks like we've scrambled things up. Here are the costs, undiscounted costs and discounted costs, with the discounted costs coming up upwards of $12 million, and quality-adjusted life years lived. It's notable that costs continue to rise after, even though the population is very small, with particularly large and undiscounted. As expected, the discounted costs are lower than the undiscounted, reflecting the discounting that occurs to present value. So that was a baseline scenario, and then we had an intervention scenario where we had interventions which were preventing pre-diabetes. So interventions of different individuals in the population. When they became pre-diabetic, they would go, quite a few of them, instead of progressing on, would go back to this state here. And in here we also see the population declining over time, despite the presence of this pre-diabetic prevention. People are aging, and there's some hazard associated with death that continues to be applied. But what's notable is that there's costs that are maybe lower from health services because we're keeping people alive for longer. But we're also facing some quite large costs associated. So maybe lower health services costs because we're keeping people healthier. But there's some quite large costs associated with interventions, both the screening and the lifestyle changes up here. These impose quite large costs, and the costs have actually gone up over, if I'm not mistaken, over the baseline. So given that we have such a model, this session focuses on the issue of well, how can we perform a simple cost-effectiveness calculation, looking at, say, the incremental cost-effectiveness beyond baseline associated with an intervention, say associated with this intervention, associated diabetes prevention. Given that we can run one and that we can run the other and kind of eyeball it, how can we actually have a scenario which would actually compare the two and compute, say, an incremental cost-effectiveness ratio? So we're going to build exactly that here. So to do that, we're going to take this model, and I would welcome you to follow along here. And we're going to add in an experiment. And this experiment is going to be incremental cost effectiveness calculation, and it's specifically for aggressive intervention. Now, this is going to be a parameter variation experiment. And that's because parameter variation experiments, in contrast to classic simulation experiments, a parameter variations experiment can run the model many times. And here we're going to, in this particular case, run it twice, although we'll use a mechanism that can generalize through that. Why twice? Well, once for the baseline and once for an alternative intervention scenario, the scenario with the same parameters here. Okay, so we've just created such an experiment. This experiment again is distinguished by the fact it can run the overall experiment several times. Now, run different scenarios. So we want to simulate a baseline and we want to simulate an intervention scenario. How are we going to do that? Well, take into account the flexibility within AnyLogic of this incremental cost-effectiveness ratio, of this parameter variation experiment. We indicate freeform, meaning that sort of we'll take care of giving an expression to compute these values for different iterations, that is, successive runs of the model. These will be here successive scenarios. And we'll run a number of two runs, one for the baseline, one for the intervention. Now, for each successive run, it needs to know what to assume for the discount rate, what to assume for the chance of per unit time of going back from, given that someone has prediabetes, for recovering from it. What should we do for the cost per year for screening or for lifestyle interventions? Well, okay, we're going to put in some expressions for these things. A thing to note here is if we click down here, AnyLogic helpfully puts up this indicator here, which indicates that we can actually find out the iteration number. In other words, whether this is the first time we've run the model or the second in this number of runs, in these two runs, whether it's first or the second. And this goes 0 and then 1. Going up, if we had 10 runs, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it's telling us within this area, index gives us the iteration number. So we can put an expression here that, based on the index, tells us what value to use. Now, we want these values associated with the intervention, this chance of recovery, these sort of screening per non-diabetic screening cost, and per pre-diabetic lifestyle intervention cost to be 0 for the baseline, but we want it to be something else for the intervention scenario. So let's go see what the values are in the intervention scenario you want to use. Okay, it's 0.25 for the case of this this hazard, and then it's 205,000. So the art here is going to be how do we incorporate those? How do we make this, for example, this value of the recovery chance per unit time to be 0.25 if the intervention scenario and 0 for the baseline? Well, Java has a little bit of syntax, so we could say, well, if index, where did that index come from? Well, remember, that was the thing that was telling us was available. It indicates the iteration number. So if the iteration number is number 0, then use 0, otherwise use 0.25. Why 0.25? Well, that's the value that we want to obtain when we're looking at this aggressive case. We're going to use a very similar expression. Now, to be safe, we'll put this in parentheses in case it's next to something else. Okay, we're going to use a very similar logic here for the costs on a per non-diabetic basis for screening. It's going to be 0 for the baseline, 200 otherwise, and for the lifestyle intervention cost for pre-diabetics, it's going to be 0 if it's a baseline, 5,000 otherwise. Now, if we wanted to investigate many different alternative scenarios, we could do so. We'd want to use a more general form than this. We'd probably call off to a function that switches based on the index and returns the appropriate number here. But for simplicity, I've kind of put it here. So this is the first thing we want to do. In other words, this is telling AnyLogic in this particular expression what values to assume for each parameter based on which iteration we're considering. Okay, this is great. This will actually allow it to run successive iterations, which may run in sequence or it may run them in parallel using multiple cores. But this is not all that we have to do. We have to do more than this. Right now, we may run this thing with different values for these parameters, but we're not keeping the values anywhere. We're not saving them up. So to do that, to save them up, we need to create some structures within this experiment. We have to create some structures that will save away the values for each successive iteration of the model we run. In other words, each successive scenario, the baseline, in this aggressive intervention, we want to remember what the results were, so that when they're all done, we can compute the incremental cost effectiveness ratios, for example. So how are we going to do that? Well, a kind of nice way is if you drag in these collections, create a collection for each of the things that needs to be saved away. To compute those incremental cost effectiveness calculations, suppose we want to compute, say, the discounted dollars per quality adjusted life year saved, the extra dollars required for that intervention beyond the baseline for each successive quality adjusted life year saved. Or maybe we want to consider it in terms of discounted or undiscounted values, or maybe in terms of life year saved. So let's give ourselves a little bit of flexibility here. It will sort of illustrate the principle. So we're going to save away for each successive scenario the value of life years. So I'll say life years for scenarios. Now I'm kind of running afoul here of Java's naming convention, normal naming convention, but because life years is capitalized normally, I don't want to make it lowercase. This is going to be a collection. So I dragged in from a collection over here. It's this collection area. And so we have this. I dragged it in, and we'll leave it as the default to so-called array list. That allows us to flexibly add values, but these will hold doubles, okay? And just to kind of illustrate this again, I'll drag another one in. We could have copied and pasted that one. And this will be quality adjusted life years for scenarios. What's going to live in here? Well, for each successive scenario it runs, it's going to put values in here. Each successive scenario it's going to run is going to put one value in each of these. It's going to remember, say for the baseline, what the life years lived by the end of that run was. And it's going to put in a value to the life years for scenarios to remember that. Similarly, for qualities for scenarios, it's going to look after it's finished that baseline. It's going to take the value for the qualities lived across the entire scope of the scenario, and it's going to save it away here. Okay, and similarly, we're going to create similar collections for these other two here. Now, maybe what I'll do is just to show you another way to do this. You could do a copy paste. And oh, now where is it gone? That's the problem with copy paste. Sometimes it's not obvious where it is. Okay, here it is. Come on. Oh man, put it way down there. This is one of AnyLogic's weak points, I gotta say. So come on, get it up here. Okay. So by the same sort of token, we're going to need to remember this. Accumulated discounted costs, okay? So this would be accumulated discounted costs for scenarios, you know? That also is going to be a thing of double. And then I'm going to, let's see, can I don't think it allows me to, oh, it does, Control, click, and drag does a nice job with that. Okay, I'd forgotten that. So this would be, so I just copied it through Control, left click, and drag. Maybe Command, left click, and drag on Macs. I can't remember. Okay, so here we have accumulated discounted costs, accumulated undiscounted costs for scenarios. And each of these is a collection. We're going to be storing away values for each successive scenario in them. In these, okay? We'll kind of leave it like that for the moment. We'll come back and add a bit of structure in just a few minutes or so. But let's go down here and let's actually wire things up so that these values are stored away. Okay, now sort of there be dragons. We're getting into one of the more tricky areas of AnyLogic. I would invite those who are interested in understanding this better to look at my lectures on calibration or on parameterization within, on sensitivity analysis within AnyLogic. Okay, so what we're going to do here is we have to insert values into here for each successive scenario. And we have to do that just after the scenario is run. So after we've run an iteration and run a scenario, we want to rescue, to salvage the values from there. Which values? Well, we want to salvage these values up here. Before it disappears, we want to read those values out, because after all, it's going to throw the whole thing away and then run another scenario and throw that away. It's going to create this main object, run it, and unless we pull those values out, they're going to be lost. And so we got to pull them out after it's run, but before it's disappeared. And this is the place it disappears. That's the place to do it. You'll notice, once again, AnyLogic is given some helpful hints. It says use root to indicate the root active object. Now that may seem bizarre computer science terminology, and it is kind of. The basic idea is root tells us the current main. It's the main that just finished running. The main object that just finished running. We can ask, for example, what is its life years that it accumulated? We can ask, okay, so what are the accumulated life years over the entire time? And let's insert those into these collections. So here we have a collection. This is, we're doing this in the experiment. This code is all down in this experiment. So we have these things here. We can just add the value in, say for this life years collection, we'll add the value of life years from main, the final value of life years that resulted from that run of that scenario. And similarly for qualities, we'll add in root qualities. So where am I getting these things from? Well, it's just these things here. Okay, and then similarly this accumulated discounted, we'll do the undiscounted one first. We want to add into that collection. In other words, have the collection remember for us root dot accumulated undiscounted costs. Okay, just reading the value out of that, and then into the accumulated discounted costs, you want to add root dot accumulated discounted costs, okay, from main. So we're rescuing these values. For each successive simulation run, we're going to be rescuing the value from main at the end of that simulation and putting it into these collections, because right after this gets done, very shortly after the main disappears. It ran, it enjoyed its time in the sun, and it disappears. And if we don't rescue it, it's going to go away. So we need to rescue it and put it into each successive thing here. So let's just illustrate this process. Let's run this. I should note here that what do I mean by each successive scenario? Well, probably many of you got it, but to emphasize, remember we said to run 2 runs. We could have said run 10 runs if we, it would have made sense if we had provided different values for scenarios, and we could have added a value in for each of those 10 runs, so each of these would have 10 runs by the end. But let's go do this. Each should have, after it's done, each should have 2. And so this pops up. Initially of 0. We have to start it up here. And you'll notice that things are happening. It's actually running the scenarios here. It's trying to run them flat out. There's in this parameter variation experiment, there's no graphical display of model operation. Instead, we just have an indication that it's running. Why 2 bars here? Because my machine on which I'm running this has 2 cores, and they're proceeding in parallel, as they can. They're independent of one another. Okay, so it's going faster and faster as the population is smaller, and boom. Okay, so after we've run this, now we have, from the 2 scenarios, we have life years lived. Not surprisingly, in the baseline, they're smaller than they are in the intervention. We have qualities for scenarios. Not surprisingly, they're in the baseline, they're smaller than they are than in the intervention. The intervention not only extends people's lives, adds years to life, but it also adds life to years. It keeps them in higher functioning states and with higher quality of life. Similarly, for the discounted costs, there's a difference, and in fact, the discounted costs are in fact higher for the intervention, because we do have large intervention costs, most notably, and similarly, undiscounted costs are higher as well. So we do have gains in life years, quality adjusted life years, but in other words, the intervention scenario is favorable there, but we're worse off in terms of costs, or at least we're bearing higher costs. We're extending people's lives. They impose costs over the length of that life, and then are more, but more to the point, we have large intervention costs. Okay, well, that's all well and good, but we could easily export these things to Excel. I should have shown, copy them or what have you, but let's actually perform the cost effectiveness calculation here. So let's pull in a variable that we'll assign, and this will be incremental cost effectiveness, incremental, say, discounted cost effectiveness, or let's make this incremental, so this will be cost per quality, incremental discounted cost per quality. Forgive me for sort of casting around for names there. I like names that are descriptive. They more than pay themselves back often in terms of clarity. Okay, so incremental discounted cost per quality. And then we could have a similar costs associated with undiscounted. Now, one thing I'm not doing in this model is sort of discounting qualities, and I could readily, forgive me for not going back and doing that right now. But here we could have an incremental undiscounted cost per quality. And these quantities we could compute from, say, differences in these guys between the scenarios, or excuse me, differences in these guys. We could similarly have incremental discounted cost per life year saved, life years lived, per life year lived, and we could similarly have an undiscounted cost per life year. So here we go. Cost per life year. Okay. Okay, great. So we've associated variables with these. Now, let's go and assign to these variables. I mean, right now they're ready to do their job, but where do we tell them what to do? Well, this is all taking place within this experiment. Remember, this parameter variation experiment, and we've got to tell these things to compute basically when it's done. That is, when it's gone through each of the number of runs. Here it's 2, but in general it may be larger. We want this thing to do its job. Okay, so let's go to advanced, and the place that this will be done is when we'll check after each iteration, hey, was this the last iteration? If so, then we can compute these things. In this case, it's just the second iteration. Clearly, if you're doing many iterations, maybe you do each with respect to the very first, so you could compute, different cost effectiveness ratios of successive scenarios. So how are we going to tell if this is the last iteration? We want to tell this, hey, if this is the last iteration, I want to compute these quantities using these guys here. This is, we can ask, okay, well, what's the current iteration? We can get that number. You'll notice this get current iteration returns the iteration number 0, 1, 2, etc. And we could check if this is get max. Is it is this the same as the max? Oh gosh, this thing is behaving truculently. Let's see if this still works. Yeah, okay. Okay, here. So if we start to have get maximum iterations, this tells us that's what we want. Get maximum, and I don't know why it's not iterations. Oh, I see why. Classic rookie mistake. So now it was complaining. It was confused. Okay, get maximum iterations. Okay, if this is the last one, in other words, if we have 2 iterations total, and this is not number 1 but number 2, that's when we can do this work. Now, I could put some code in here to do this work here. This is one thing where I'd really like to do, like to write a function. Folks, there's only so much I could do things in kind of a sloppy way just for pedagogy, and really this is like a classic case where it'd be really nice, conceptually nice, to not stuff code into that place we were just at, but to instead put it in a function which has a nice name to it, can be easily seen by someone coming to the model. So perform cost effectiveness calculations. So that's the name of this function. Okay, doesn't need to take any arguments, and we can now go back to where we were, and we can have a call to it. Okay, so here we go. We could call off to perform cost effectiveness calculation. If this is the last iteration, go do it. And we're not going to put in the exact code here and hide it there. We'll put it in a place that gives it the stature it deserves. Okay, so this is the place where we're going to perform these things. Okay, so let's go through and perform each of them. It's rather simple. Had I my druthers, I had a more general mechanism, and some languages would be very nice to do so. But let's let's deal with these one at a time. Okay, and we'll just put in the code directly here. Not try to capture all the patterns in it. Okay, incremental cost per quality. Okay, so what do we have to do to compute this? Well, we want to compute cost per quality, so we're going to have some cost divided by qualities, and it's the incremental cost. So the costs associated with the intervention scenario minus the costs associated with the baseline. So the extra costs imposed by the intervention scenario. So what are those costs? Well, this is discounted, so we want accumulated discounted costs for scenarios. And we want to get it for the intervention scenario, that's scenario 1, and subtract off it for the baseline scenario, that's scenario 0. Okay. And then, so this is the extra costs borne by the intervention, which lives in second element within here. It was not element 0, but element 1. We're subtracting off from the value for the corresponding value for the baseline. And we do a similar thing for the denominator. We take the qualities for scenarios, and we get the value for the intervention scenario, and we're going to take off the value for the other scenario, for the baseline scenario. Okay. We compile that, and it's all quite good. So so we can now kind of go to town in a similar way, do discounted cost per quality, and that's going to be similar. The denominator is actually very similar. In fact, the numerator is textually quite similar. It's just we're dealing with undiscounted costs. So accumulated undiscounted costs for scenarios. And I just checked that it's spelled correctly there. And we divide it by the incremental costs in qualities. Oh gosh, there's these repetitions going on. So I'll make this clearer. Double incremental qualities. I don't like just repeating code in this sort of way. It obscures the commonalities. It just leaves it ripe for errors. It means you have to fix it in multiple places. You may forget one. Okay, so there's incremental qualities. Incremental discounted costs is this. So here we're just assigning some variables. Discounted costs is equal to this. We're just giving sort of nice names in essence to these different scenarios. We can have incremental life years. It'll just be life years for scenarios, and then incremental undiscounted costs. Okay, so here we have undiscounted costs, and conceptually, I know this looks like you're putting things off, but it makes the formulas just much nicer. So discounted costs per quality, it's just incremental discounted costs divided by incremental qualities. Isn't that easier to understand? And similarly, okay, undiscounted costs, let's get rid of this monstrosity. So undiscounted costs, incremental, okay, it's just incremental divided by incremental qualities. You see it captures the sort of commonality and structure much more easily. And so here we have that, and then to do corresponding things for the life years. Okay, no, this says, okay, this is for life years, and this should actually, oh gosh, look at that. One does say qualities, one says quality. We should really make them consistent. So this should be incremental life years and incremental life years, just to convert that to life years. Yeah. So undiscounted. So this captures this better. Okay. So what are we doing here? Well, basically what we're doing is we're taking incremental qualities. We're just taking the the first element minus the second element minus the first element. The thing in the 1th position minus the thing in the 0th position. In other words, the second minus the first. In other words, the difference between the intervention scenario here and the baseline scenario here. Similarly, for incremental discounted costs, we're doing the same thing here. So we're taking the difference between the baseline and the intervention, the baseline. Now, I don't need these extra parentheses around here, since they're nicely sort of separated out anyway. So I'm just going to get rid of these parentheses, and, a little bit less clutter. And now we've assigned to it. Now, what we have to be careful about is that this guy is not spelled consistently. Consistency is a virtue in many things in life, and one of them is in naming. So let's try to compile this. So we'll probably have errors. Oh, it doesn't have errors. Oh, okay. Well, that's kind of nice. So it looks like it's a happy camper. Let's just look at this. So discounted cost, discounted cost, discounted cost, undiscounted cost, undiscounted cost, discounted cost, discounted, undiscounted, discounted, and then it's per quality. It's divided by quality, per quality, it's quality, per life year, yeah, per life year, yeah. And this is qualities. It's a difference in qualities. Discounted cost, difference in discounted costs. It's a difference in, let's make sure that it's right in a second, in discounted costs. And the second one as well, it was over here. Differences in life years, differences in undiscounted costs. Yes, differences in undiscounted costs. Okay. And all these are 0 here and 1 here because it's the intervention minus the baseline. Okay. So, again, just making sure that we're in good shape. Well, folks, now we can assign to these functions. And I could have a fancy display of it or write it to a database or whatever, but let's just run this thing. So before we ran it and it populated these scenarios, what's the difference going to be this time? Well, now it's going to run it. And at the end, instead of just presenting us with kind of what was accumulated there, which is good for exporting to a spreadsheet or something like that, now we're actually writing to these variables here. We're actually putting values into the variables at the very end of simulation after that last iteration. Okay, things are going faster and faster, so there's fewer people in the population in each of these scenarios. And now it's about to be done, the final thing, and there it goes. It spits out these discounted costs. And again, I've kind of violated many conventions in dealing with this because I didn't discount qualities, for example, and we could very easily add that into the model. But I must say those are rather favorable cost-effectiveness ratios. So what we've just shown is how to build up a model. If in this particular session, how we've added an experiment which uses these measures, these health economics measures that are calculated on a per scenario basis within Maine. These things like cumulated undiscounted costs, cumulated discounted costs, qualities, life years, etc. Both the latter being undiscounted. And here we have a scenario which actually runs the model twice, once for the baseline, once for the intervention scenario. And as part of that, at each successive run of those scenarios, and it could be, instead of 2, it could be 10, each successive run, it saves away information on the outcome of that scenario. And then once it's done with all the interventions, this is where the key check takes place, it actually performs the cost-effectiveness calculation. And the cost-effectiveness calculation, as we've seen, uses the values compared in the intervention scenario and takes their difference from the baseline scenario, and it actually uses those to compute these values here. So now we have a model where we can not only accumulate sort of many classic health economics quantities, but we can actually have a scenario that runs intervention and baseline computes the incremental cost effectiveness ratio. All this within an agent-based model where people evolve over time, evolve in terms of quality of life, in terms of the costs, and where we're also simulating interventions which secure improvements to health and quality of life by forestalling diabetes, for example, allowing people to live the full length of their life, for example, without diabetes by helping pre-diabetics recover. But where those interventions also impose costs, both screening costs and costs for achieving lifestyle change. I hope this information is of help. I would again urge you to refer to the part 1, and in fact it was part 1 and part 2 for this exercise prior to this video, because it will help you understand the base model in which you're building things. But I hope this has been of help, and I'd welcome any feedback. Thanks so much. Take care.